is a second lab for Lab 5 on classification. The last time we talked a lot about the structure of learning, and we did it in the context of regression. Your homework 3, is on classification, so I thought we should record this additional lab to go over the basics of classification. The difference between regression and classification is that in regression you are looking for a continuous output y, so y can take real valued values. Whereas in classification, it's one of a bunch of things. So typically, if it's like a one thing or the other, spam or ham, red or blue, it's a 1-0 classification, and you'll typically encode it as a 1 or a 0. If it's not, then you might encode it as a 0, 1, 2, 3, 4, 5, or something similar to do multiple classification. We won't talk about multiple classification here, but you can look at the scikit-learn docs for how to do it. Okay, so the basic idea behind classification is kind of in this diagram over there, where what we're doing is we have two things of different colors, and they are in some part of your feature space. Here's an x and a y. They could be any two things. They could be like, for example, in the problem we did last time, the religiousness of the people in a county versus the poverty of the people in the county. And you might be looking at Democrats versus Republicans, very conveniently coded blue and red over there. And you want to draw a line, or if you don't want to draw a line, maybe you actually want to sort of get the structure of the clusters, the red cluster and the blue cluster. There are different ways to do it, but one way is to draw a line. Logistic regression, by the way, is a model which actually draws a line for you, and we'll look at that in a little bit of detail before going on to k-nearest neighbors. So it's just some boilerplate code to do plots over here, which I'm just going to skip over. And go to our example here. Our example here is an example of heights and weights of males and females, and we're trying to separate these people out into males and females based upon their heights and weights. So we're going to read it in, and once we read it in, remember we talked about last time that the structure that scikit-learn expects data in basically is a bunch of samples. So each one of these rows corresponds to a sample, essentially. And each of the columns over here is a feature. So in this row, this is feature 1, feature 2, feature 3, feature 4. So for example, that could be heights and weights over there for the first person, heights and weights for the second person, and so on and so forth. And if you had other attributes of the person, like maybe nasal structure, that would go there, or hair, that would go there, and so on and so forth. So that's the structure that scikit-learn expects your data in. And the response, whether it's, say, 1 for male, let's go males as 1 and females as 0 over here, then you'd have 1, 1, 0, 0, and corresponding to whether the person is a male or a female. We can do a little scatter plot of this, just to look at our data. Always visualize your data before doing anything. And you can see that there is a sort of, as you might expect, there is a bit of overlap in this plot, in this intermediate regions of heights and weights. But otherwise, the females are mainly to the left over here, and the males are mainly to the right. Not surprising. You would know this from intuition. But let's try and make a classification for this. So I'm going to show you 2 different ways to do this, and this will give you a basic idea of how classification happens in scikit-learn. Here's the first way. I'm going to skip over this first cell out there and just go to the third cell over here and explain what's going on from there. So if you remember, Joe in class talked about regularization. And when you do logistic regression, you also add in a regularization term. It's an L2 regularization. So it regularizes the squares of the coefficients. It's trying to keep the squares of the coefficients small. And the regularization coefficient is the C. And what we want to do is treat the C as a hyperparameter. And so we're going to try different C's in our classification. So the first thing we need to do, let's go to the cell above, is basically split our data. So we're going to split our data into a into a training part and a testing part. And what I've basically done is I've taken the values of those 2 columns in Pandas. So you know that doing this in Pandas gives you a data frame, a smaller data frame. And if you adjust to the values, it'll give you the data in the form you need for scikit-learn. You don't have to do anything else. That's the end of it. It's really simple. In fact, you don't even have to do the dot values. If you just take that little data frame, scikit-learn will know what to do. But I've just taken the values here to show you. And then what I've done over here, so that's the x. So train test split always takes the x first and then takes the next thing you want to split, which is the y here. And what I want to do over here is I want to get a y, which is the gender equal to male. So when the gender is male, you're going to get a 1, and when the gender is female, you're going to get a 0. So these are a bunches of 1s and 0s, and I'm taking the values of those. You'll get a bunch of 1s and 0s. And once you get the 1s and 0s, I'm going to split that using train test split. And I think typically the train test split does a 75-25 split. I don't remember. You can look at the docs. But so this splits the data for you. And it splits the data into 4 different parts here. The first 2 correspond to the first argument you put in there. That's the training data set, and that's the test data set of the features. That's the sub-data frame, if you like. And then you have the response. Here's the training response, and there's the test response. Okay, so now that we have the training set and test set, let's go ahead and actually do this classification. So we import logistic regression from linear model. We set a max score to be 0 for the time being. And then for each one of these C's, so for each one of these things, it's a separate model, so we're going to do a separate model. So for each one of these over here, we're basically using this function cross-validation score, which is actually going to do the entire classification for us and is going to give us a cross-validation score as to what's the sort of error, if you like, or what's the accuracy, depending on how you want to do it, from the classification process. Then what I'm going to do is I'm going to ask if the score is greater than the max score. If the score is greater than the max score, I'm going to update this, and I'm going to set the best C to be that particular C. And at the end of this entire loop, what's going to happen is I'm going to get the one of these models, 1, 2, 3, 4, one of these 5 models, which actually has the best score of these. So in this particular fashion, and in all of scikit-learn, you'll actually be looking at scores rather than risks or errors, but you can also get scikit-learn to look at risks and errors if you like. So here, when you have scores, greater is better, so you're looking for a model with the highest score. And when you find the model with the highest score, you're asking it to also print out the best C. And when we do this, we find that the highest score is 0.9, and the best C is 0.1, which is somewhere in the middle over here. How did I do this classification? That's the job of this function up here, the CB score function. What it does is that it takes this classifier, this logistic regression classifier, with the particular value of C that I put in there. Okay. It takes that classifier in there, it sets the result to 0, and it sets the number of folds you're going to do the cross-validation onto 5. It uses this function from sklearn.cross-validation called kfold, and what kfold does is that it basically takes the size of the array and splits up the indexes going up to the size of the array into n folds. So it's going to say, so here if the size was 1,000, it's going to split 1,000 into 5 folds, so it's going to have this is basically going to give you 5 folds of size training and testing out here. And since this is 5-fold cross-validation, if I have 1,000, it's going to do 800 training and 200 testing. And so once it does that, basically, it's going to give you 5 of these, since there's 5-fold cross-validation. So this loop will go 5 times. Each time in the loop, it's going to take the classifier, which is the logistic regression, with that particular value of C. It's going to fit the training data. Remember, these are the indices, so I just index the arrays x and y by those indices. It's going to take the training data. It's going to fit the x and the y. Remember that if you remember the fit, this is always the interface for fit in scikit-learn. You always have the x stuff first, the features matrix here, and the response matrix there. So it's going to fit this matrix. And then what it's going to do is it's going to take the test data. On the test data, it's going to predict what's going on. So it's going to take the test features. It's going to predict that. That's going to give you a set of y's, the prediction, the predicted responses. It's going to take the score function and calculate the score of the predicted responses with respect to the actual values of the test responses. It's going to add that to the result. And then it's doing this over 5 folds, so it's going to basically average this result over the 5 folds. So this is sort of like, this looks like it's really complicated, and it kind of is. This is not the easiest way to do it in scikit-learn, but you can see the structure of what's happening out here much more clearly. What I'm doing is I have 5 folds, I'm going over the 5 folds, I'm adding to this result accumulator the value of the score function each time, then I'm dividing by the number of folds to get the average. So when I land up doing this out here, I get the average score for that one particular C. And then I do it for my different values of C. It turns out there are 5 values of C. So, and then finally I get the answer. So you can see what it's doing, that for each value of C, it's doing 5 folds. It's actually running 5 classifiers. It's averaging the results from the 5 classifiers. It's giving me a value for the C. And then it's running it over 5 values of C, and it's picking the maximum score. And that's 0.1 over there. What you do then is, if you remember what's happening in these k folds over here, it's taking it's taking this y dot size over here, and the y that you're putting in over here, you can look over here, is this XLR and YLR over here in the CV score function. It's these two. These, if you remember, came from the train test split. So there was a further train test split going on in here, and this is really your train and your validate split that's going on in here. So it's doing this train validation split, and it's training your model on the training set and the validation set, and once it's done that, basically, it spit out the parameter C you should use. So now you create a new classifier, and the new classifier, you basically take the best one you got from that whole loop, and now you fit it on the entire training data. We don't need to take a hit now. We've already done the validation. We've figured out what the best C is. So we're going to run this now on the entire training data XLR. And we're going to have a classifier that's fit on that. And then we're going to make predictions with respect to that. And then we can ask what the accuracy is. And you see the answer is about 92% over here. So the accuracy score, by the way, over here, which is what is being used to run this thing, you can see that, I suppose, over here, let me see where it is exactly, in the function above, where the accuracy score is the default score. All the accuracy score does is that it finds out how many of the predictions were correct. So if you got a prediction, if the actual test value was 1 and you predicted it to be 1, you add that to the accuracy score. If the actual value was 1 and you got a 0, you don't. And then you take a mean of all of those, and basically you're going to get a fraction of the accuracy, and that's the 0.92, which you see. So I said this was a slightly complicated way to do it, and it is. Here's a way, way, way simpler way to do it. And it uses Grid Search CV, which is this Grid Search cross-validator interface. I talked a little bit about this interface in the previous lab when I talk about regularization. We didn't get the chance to actually go over regularization in the spoken lab, so you'll need to read it. But what Grid Search CV does is that it actually does that entire process for you. So I basically initialize a logistic regression classifier. Notice I don't put the C in here at this moment. Instead, I put the C in a dictionary whose key is the hyperparameter and whose values are the list of values I want to test for that hyperparameter. Here I'm testing 6 values. If you had more than one hyperparameter in your algorithm, which is true of decision trees, SVMs, and many, many other algorithms, then you would have another key in this dictionary. Say the other one was gamma or something. You'd have gamma, and you'd have a list corresponding to the parameters for gammas. And what Grid Search CV does is it basically goes to each point on this grid, and on this parameter grid, and it actually runs the classifier for you. It's not necessarily the best way to do it. There are sort of more randomized ways of doing this. So I'll let you look at the scikit-learn docs for the different kind of cross-validation schemes they have in it. But what Grid Search CV does is it basically takes the classifier, it takes an argument param grid, and you put the param grid is equal to this sort of dictionary of parameters over there. It tells you tell it how many folds you want to do the cross-validation on, and you tell it how to do the scoring. The default, by the way, is accuracy, so you really don't need this, but I just put it in to show you that you could use something else to do the scoring. That's, by the way, an interesting part of machine learning, which we'll come to a little bit later, that when you train data, you will use a particular kind of risk to train the data. For the logistic regression, it's the log loss. For SVM, it's the hinge loss. And then when you actually want to do cross-validation and check stuff on the validation set and test set, you might use a completely different loss. So in reality, in machine learning, there are 2 losses. The first loss is sort of the training loss or the probabilistic estimation loss, and the second one is the decision loss. And we'll come to that more in the next lab. And I think it'll be done in class next week as well. So anyway, just an aside, you don't have to necessarily put this parameter in. It'll, by default, it's accuracy. And so what it's going to do is going to fit these models, and notice the interface. It's the identical interface to what you had up there, where you did this logistic regression fit in the CV score above. I can just show you that again. It's the identical fit interface there, except that now you're doing it with this rather bizarre-looking Grid Search CV model over there, which somehow or the other has taken logistic regression inside it as an argument. So what this actually does for you is that it does the entire cross-validation fit. So it actually goes over the 6 of the parameters, the 5 folds for 6 of the the 5 folds for each one of the 6 parameters, i.e., it does 30 estimations for you. And it's the same interface. This is what makes scikit-learn so nice. It's exactly the same interface. Once you do that, you can print out some things. You can print out the best estimator. You can print out the best params. You can print out the best score you got. And you can print out the scores on your grid. And you can see you get some incredibly useful information from this. And that's why I suggest you use this over the other one. The other one's useful if you want to do your own thing. So over here, this is the best model. It actually smacks out the model for you. That was the best model to use over here. And you can notice that the parameter was 0.1 as we got earlier. So it smacks out the best parameter as well. It gives you the score. And even better, it actually tells you that for all of those 6 different C's that I put in, it tells you what the scores are. And you can see that the mean of the scores was 0.91, 918, blah, 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 blah. It's not that different, essentially. But what it does for you, and in fact, it actually looks like it's within the sort of variance over here, but I'm assuming there are more digits, which is why it chose 0.1. It looks like the value of C really doesn't make a huge difference in this particular thing, except when you go to very low C's. Oh, there's one thing that you should remember in scikit-learn. The C is not the coefficient of the it's not the coefficient of the term which regularizes. It's 1 divided by that. So if you have high values of C, they don't correspond to larger values of regularization. They correspond to lower values of regularization. So this all means lower values of regularization, telling you that this problem with just 2 features doesn't require much regularization at all. Anyway, that's an aside, but what it gives you is it gives you these values, and it also gives you a standard deviation for each one of these values. So it gives you 2 things. It gives you a notion of how good your cross-validation was, but it also gives you a notion of the error on your cross-validation accuracy. So it's a question of what the mean value is, but also how much you ought to believe that mean value. Okay, so we're going to play the same game. We create a new classifier, which is now basically the best params of C. We put that C in. Now we fit it in the entire training set. The split between train and validation was done by this grid cert CV inside, so you didn't even have to see it over there. So this now basically fits it on the entire training set, tests it on the test set, finds the values in the test set, and gives you the accuracy score between the actual test set and what you predicted, and it's 92%. Okay. So that's the story of what's going on in scikit-learn and classification. And this should help you quite immensely in doing your homework and, in general, writing classifiers. If you remember, in the last lab, we talked about a risk that we used for regression, and that was this mean squared loss kind of risk, where we just took the value at each point minus the value of the function we were trying to fit, squared it, and summed it over all points. And this was within the scheme of things which we call empirical risk minimization. There's exactly the same thing is going on here. Even though scikit-learn couches it in terms of accuracy, what it's actually trying to do is to minimize this 1-0 loss. And the 1-0 loss is this rather bizarre-looking symbol 1h not equal to y. And what that symbol means, basically, that if h is not equal to the true value of the point y, penalized by 1. And so if you do that, then the risk basically adds up this loss for each one of those. And when it's equal to the true value, so when the predicted value is equal to the true value, then you penalize by nothing. So thus if 5 out of 50 samples are misclassified, then the risk is 0.1. This of course means that 90% were accurate, and that's called the accuracy score or utility, and it's what we've been outputting up here. Okay. The word utility, by the way, comes from economics, where all rational agents are supposed to maximize their utility and so on and so forth, but it's the opposite of cost over here. Okay, so with that under the hood, let's go and do a real example. And this is an example where what I did was I went out and I scraped the web to find pictures of dollars and find pictures of checks. And then I decided to pretend that I'm an ATM. And this ATM's got to figure out which one of these things is a check and which one of these is a dollar, basically, because you don't want your ATM machine to think that the check for $1,000 you put in there was actually a $10 bill and make you lose all that money. So this should actually back up what Hans-Peter did in the lecture. It's an example which actually uses PCA to reduce the feature space, and then actually uses k-nearest neighbors to do the classification. So in this example, you're given a set of 87 images of checks in dollars. each of which has been scaled to 322 cross 137 pixels, and where each pixel has 3 color channels. So you can actually look at what this data size is, so to speak, and you'll see that the data size is it's quite big. The number of features is 132,342. It's just a multiplication of this times 3, right? Because those are the number of features you have in this problem. And I can display some of these images we have. So here's a check. And there's a $500 bill. That check was for only 45, so the result would have been in the opposite direction of what I said if I had taken these two notes. But you see the problem with these straight away. By the way, to do all this kind of image manipulation, you need to do some standardization. So one of the things that was done is that all these images were standardized to the same size. This lab, by the way, was inspired by a similar example on the YHAT blog. You should go check out the YHAT blog. It's actually a really good machine learning blog, and you'll learn a lot from it. So what's going on here? So you have 322 cross 137 cross 3 features. That's 136,452 features, right? That's a lot of features. Having too many features can lead to overfitting. Having too many features can lead to problems with the curse of dimensionality. And you don't want this to happen. You've seen this before, right? In the polynomial regression we did, there were lots of features. And when we had lots of features, we had those incredibly wiggly polynomials doing their thing. So we don't want so many features, basically. I think one way to look at it, which is kind of a nice way to look at it, is that we have 85 of these checks and dollars to classify. But for each one of these, we have 136,452 features. This is way more features than data points in our data set. And because there's way more features than data points in our data set, there is a high chance that some of these attributes will correlate with having a dollar or a check. So it'll correlate with the Y purely by chance, purely coincidentally. So you can see, of course, that this tells you that big data helps you in combating overfitting. And with big data, overfitting is not as much of a problem as it is with smaller data. 85 is really small data. But we have lots of features. And with so many features, there's a high chance that a few attributes will correlate with Y purely coincidentally. There is a lab that Chris Beaumont did in the 2013 cycle of this class, which actually talks about this in great detail. You should go look at it. And it actually has some information which is kind of useful for homework 3 as well. Okay, so we need to do something similar with what happens when you do regularized regression out here. We need to reduce the dimensionality. So what we're going to do is we're going to do PCA. And as you know, PCA is basically an unsupervised learning technique. And the idea behind PCA is kind of captured in this diagram. Here's some data. At this point in the data, you see that this line which is rotating is kind of perpendicular to the data. And at this point, it's now coming in to be parallel with the data. And you see two things that happen. Look at these red lines. As this line becomes perpendicular, let's wait for it. There we go. The line becomes perpendicular. The length of these red lines is incredibly long. Okay. Now, let this line rotate to become along around these pink things there. And when we do it, we can actually see that the length of the red lines becomes incredibly short. Well, what's happening? Most of the variation of this data is in this direction. If you were to rotate the axes that you have, these axes, such that the axes are rotated along with this rotating line now, so there, you would actually capture most of the variation. So what you're basically saying is that most of the variation of the data is in that particular direction. And you can see that the perpendicular direction, the error is the highest. So by going in this particular direction, I actually reduce the size of these red things as well. And that makes the error very, very much less. So if I was to rotate these entire axes to be like that, what's going to happen is that I'm basically reducing the dimensionality of this problem from a two-dimensional problem to a mostly one-dimensional problem with some noise around the one dimension. So this is the way PCA works, basically. It does these rotations into the directions of the most variation, thereby basically reducing the dimensionality of the problem. Now, you should note that this dimensionality reduction is what's called an unsupervised dimensionality reduction. I didn't use any there was no notion of Y over here in this data set whatsoever. These were just the two values of X's. Now I had X1 and X2 over there. So I'm actually not using the notion of whether these pixels in these images when I do this is either a dollar or a check. I'm just going to take these features and I'm going to see if there's such correlation between these features that I can do this with much less. So that's the game you're playing in PCA. The basic idea is that, this kind of dimensional reduction is that you're trying to see if the data lives on a lower dimensional subspace. And you can do this both in a supervised form and an unsupervised form, but PCA is an unsupervised form. There is something called LDA, linear discriminant analysis, which is a way of doing this in a supervised form, which if you want to, you can go read about. Okay, so let's do this in scikit-learn. Now, as I told you, scikit-learn has the same interface for everything, so it's really kind of simple interface. So from sklearn.decomposition, import PCA. We're going to do a 60-component PCA over here, just for the heck of it. And what we're going to do is we're going to do this transformation. Remember when we talked about transforming the polynomial features from just the x to, to 1, x squared, x cubed? We did a fit transform. That's exactly the same thing we're going to do here. We want to transform the data I have into this new data x, which is now transformed by doing this rotation for us. And that's it. That does it for us, basically. It's going to fit transform the data for us, and we have x. And now if you look at it, you can look at this PCA.explained variance ratio.sum, and it tells you that these 60 dimensions, basically, that I move things into, how much of the variance of the features is explained by it. And you can see that 94% of the variance of these features is explained by it. So it's critical to remember that when you actually do this PCA, when you're doing this rotation, you aren't actually reducing the dimensionality. The dimensionality cutting comes later. So PCA just does a rotation. But the way scikit-learn actually does this for you is that it actually does it, and it also sort of gives you the 60 top ones. And so you can see that the explained variance ratio is 94 over here, and that's what I asked for, and that's what I got. If I change this number, and I can always play around with changing this number, I can see what variance ratio I get. I don't want it to be too low. If it's too low, then I haven't really captured much of the variation in my data, and I might be missing out certain parts of the data which are important to explain the y's I got. So I can look at these. I can look at the explained variance ratio, and I can multiply it by 100 to see what fraction is. And it tells me that the first axis captures 35% of the variation. Not as much as we had in that rotating diagram above, but it captures a good amount. And then there's a sort of like diminishing returns kind of thing going on, with 6% captured in the other axis, 4% in the next, 3% in the next, and so on and so forth. So the first dimension accounts for 35% of the variation over there. So we'll just create now a data frame with all the 60 features labeled PC1 for principal component 1, principal component 2. Very simple. I'm just creating a data frame with the y's, basically. And I'm setting 1 for the checks and 0 for the dollars. And then for everything in the range of 60, which is the size of explained variance ratio, because I asked for a 60-dimensional PCA, I'm just going to set that column to be equal to the corresponding column of this transformed x. It's critical to remember that that's the transformed x. You can see the transformed x over here, PCA.fit transform. Okay. So over here, I'm just going to do some kind of normalization. You can do normalization with respect to standard deviation. If you remember, HP talked about that. Or you can do normalization with respect to the entire range. Here I just do a max minus min kind of normalization. And I get the principal components, and I kind of display them for you over here. So here is a display of the components. And this it becomes a composite image, if you like, of the check and the dollar, and it shows you what it perhaps might be using to do this distinguishing. And over here, the fact that this thing is so prominent gives you an idea of what it might be using to distinguish dollars from checks. It's this prominent medallion thing that's going on, and that will help you with 35. Will explain 35% of the variance. Will help you a lot in the classification. And that's the second component over there. So what I do here is I basically plot out the first and second component for you. And you can actually see that the checks are in, there are less of them. The checks are in blue and the dollars are in red. And you can see that I could basically almost like kind of draw a line, something like this, over here. And I wouldn't do a bad job doing this classification for you. So most of it's actually getting done in these 2 dimensions already. In fact, I could just draw this, and you could make the argument that most of it's getting done even in 1 dimension. And so this dimensional reduction is incredibly useful to do this classification. So let's actually do this classification. So here's what the thing looks like. There's some red dots and there's some blue dots. And Hans-Peter explained this mostly, and I'll just go over it very quickly. In k-nearest neighbors, what you're trying to do is you're basically roughly trying to draw radiuses around a given point. And so you can see what these radiuses look like. This one's going to have mostly red stuff, so it's going to classify any point out there as red. Over here it's going to classify any point over here as B. Or this is where it's going to actually dance around from being red to blue. The size of this kind of circle matters, basically. If the circles are very large, then you're going to get a much more kind of biased regime. So what it's doing is the way k-nearest neighbors works is that it asks for the k-nearest neighbors of the training set of the new sample. So one must define a distance in the feature space. Typically, we can use the Euclidean distance, though as Hans-Peter said, we could also use a Manhattan distance if we wanted to do this. Okay, so I'm not going to go much into that since it was already talked about in class, but I'm going to just show you how you do this. And I've written a little function to do it. I'm importing k-nearest neighbors. The y's, I'm basically just getting the y as ints. And I'm just taking the first two principal components. That's why that's subdata frame. And I'm going to standardize the subdata frame here. You typically, because these different principal components may correspond to very different values, I'm just standardizing. It may actually be better to even standardize this before you even get the principal components. So it's just standardize all your data first and then get the principal components. In our problem, it really doesn't make much of a difference because it's a bunch of images with with all these sort of like pixel values constrained to be between a certain value and a certain value. So it really doesn't make a difference for us. But I'm standardizing it anyway, so it becomes simple. But you ought to really be doing this even before you do the fit transform of the PCA, which I did not do here. Okay, so to do this classifier, basically I split stuff into a training set and a test set. I'm using this line over here to do that. Then I'm going to have this neighbors, which says how many neighbors should I use? Should I just use one neighbor of my sample? Should I use 20 neighbors of my sample? I'm going to put that in here. That's, again, one of those hyperparameters of the algorithm over here. It corresponds to your C in logistic regression. It corresponds to something else, too. It's also a complexity parameter. We'll come to that in a second. And then I'm doing the fit. Remember, the fit interface is exactly the same, no matter what you do. You can say CLF is equal to CLF.fit. You don't really need to do that either, but it doesn't hurt to do it. To get the training accuracy, I can use the score function. The score function basically does two things together. It predicts. So it predicts on X, over here on X train, essentially, and then it finds its accuracy with respect to Y train. So here I'm just looking at the accuracy on the training set itself, okay? This is what we really want. We want the test set accuracy. So I'm going to get the accuracy on the test set. This does a predict on the test set, then gets those results and computes the accuracy score with respect to the Y test over there. Okay. We do that, and this is just for plotting. It's not really important. Okay, so let's see what happens. When we choose k is equal to 1, that's the neighbors over there, and do this classification, notice what happens. I get those islands Hans-Peter was talking about in the class. I don't know whether this is that well visible, but you'll see it's kind of washed out on this, but I think it'll be okay on the screen, right? When we do it, yeah. So there's actually an island around here. You should look at this in the lab if it does not come clear to you on the screen. And that happens when k is equal to 1. Now, on the other hand, if you choose k is equal to 50 over here, and you can run this a few times and you'll get slightly different results, ditto for the previous one. You see what happens because we have a majority sort of class of red over here. It's just basically occupying the entire screen. It's all red, essentially. By the way, that's kind of like a baseline classifier. It's something worth remembering. That anytime you write a classifier, if I don't do better than I don't do better than assuming everything belongs to the majority class, then I'm in bad shape. If you have a 50-50 classifier and the majority class is 51 and the minority class is 49, you're probably going to do better than that because that's just almost like purely random, 51 is to 49. But if I have a very skewed problem, as you'll see in the homework, if I have 85% of the samples of one type and 15% of the other type, remember when you're looking at, if you're working for a fraud company like a bank or something of that sort, and you're trying to look for fraud in a credit card or something of that sort, then it's almost like 99 to 1, and you need to write classifiers which are better than 99% accuracy. For mortgage and stuff, you probably need to write classifiers which are better than 84% accuracy, 85% accuracy. Similarly true for churn, of which there'll be an example in the next lab. Okay, so what's happening over here? It's kind of obvious, right? That if you take just one thing around, then you get all the sort of like roughness of the boundary that Hans-Peter was talking about by doing this. And if you take a large sort of like amount of things, then you get this kind of bias or over-smoothing process that's going on over here. So to actually do this properly, we ought to cross-validate. But before we do that, what I thought I'd do is I'd actually run fits for each and every value of k. Yeah, over here, k equal to even, perhaps I didn't need to run. And if I do that, I get a diagram over here of the test error and the training error. And you can see what happens is that, notice by the way that I have plotted this in the opposite direction, starting from a large k to a small k, because this is the bias limit and that's the variance limit. I just wanted to be sort of similar to every other machine learning plot you've seen and will see. And so you can see that the training data keeps going down. The training error keeps going down, and the test error goes down. This is rather flat area over which I think the classifier does well for all of these sort of Ks. And then the test error starts increasing as well, because you've gone over into the variance limit and are starting to overfit over here. So to do this the right way, we should do it by cross-validation, and I'm going to set up two pieces of code to do this, and pay attention to these pieces of code because they'll come up again in the homework. So this is basically optimizing a classifier over a particular parameter dictionary, over a particular X train and a Y train, or a given training set with a default of 5 folds, and it's basically doing the grid search CV with that param grid we were talking about and the CV parameter there. We are doing a fit, and we are going to get the best estimator, and we're going to return the best estimator out of it, and we just print out the best params. Okay. And then we can use this best classifier to fit the entire training set. And this is done inside this other function that we've written, which is doClassify. And what this classify does is that it takes the feature name, it takes an input data frame, and from the data frame it just takes the feature names, and this is basically a list of features, so it basically sub-data frames that. If standardize is true, I've set it to false over here. If standardize is true, it's going to actually standardize it for me. Okay, then it's just going to get the values from this standardized or not data frame, and it's going to get the target, and there are two arguments here, target name and target one val, which are the column I'm going to use as a target over here, and the value of that column that should be used for the one value, and this only works for 1 and 0 classification. Okay, so setting that up over here, and I multiply it by 1 just to get the ones and not get trues and falses. And then I do a train test split here with the training set and test set. That should be pretty obvious to you. Then I run the CV optimize function we defined above, and then I get the best fit classifier out of that, and then I use that to fit the entire training data, and then I report to you what the training accuracy was, what the test accuracy was. I print it out, and I send out all of the classifier, the training set, and the test set. So we'll have a variation of this on the homework as well, a little bit more complicated to classify, but this is a general sort of, if you like, skeleton of a function that's kind of useful to do these classifications really fast. So now we can do this really fast. Here we go. Our best cross-validated KNN classifier, the training data and the test data is obtained as the byproduct of doing this classification, which is a k-nearest neighbors classifier with a param dictionary, which takes the nearest neighbors going from 1 to 40 in steps of 2. The data frame df, which is the data frame of all those principal components. I just want principal component 1 and principal component 2 over there. I want to use the label of that thing, and I want to set the check to be 1. And that's it. And we do that, and we see in this particular case we get nearest neighbors 3 giving us the best sort of accuracy, and it's not overfit, and you can see that it's not overfit. This is something important by seeing that the accuracy on the training set and the accuracy on the test set are roughly comparable. If you see a situation in which the accuracy on the training set is way higher than the accuracy on the test set, then remember what's happening is that you are in one of these limits, basically. But the accuracy on the training set, and here I've plotted the error instead of the accuracy, but the accuracy on the training set the error on the training set is much lower than the error on the test set, or the accuracy on the training set is much higher than the accuracy on the test set. And if you see those numbers diverge over here, then you know that you're in the overfitting limit. And this is what this classifier looks like. Remember that KNN has slightly jagged boundaries, and you can see this jagged boundary go down that thing, basically. But it's not overfit with those little pock marks, or not underfit by having the entire thing red. Okay, and we can make probability contours of it, and so you can see what the probability of the classifications are. These probabilities are, I wouldn't say necessarily the best, because they're just obtained by looking at the number of things in your neighborhood. But you get some idea of where it's going to classify things quite surely as red and where it's going to classify things quite surely as blue over here. And that's sort of like the 0.6 contour over there, and that's like the 0.3 and 0.5 is in between over here. Okay. Finally, once you do this, you want to evaluate how well you did on the test set. And so you can see what we are doing on the test set over here is that we're getting 9 of the false positives as false. So 9 of the zeros are zeros. In this case, I think, if my memory serves me right, the dollars are the zeros. So it actually gets the 9 of the dollars as dollars, and it gets 8 of the checks as checks. And basically what's happening over here, I think, is that if I remember the order of this is correct, it's having one of these misclassified from being a check to a dollar. So we'll talk much more about evaluation of these classifiers later, and you can read a little bit more further in this lab about it. There's actually a good amount of more detail in this lab about the entire structure of logistic regression from a statistical perspective, which you can read if you like, but I'm not going to go into. And in the next lab, and also in class the next week, we're going to talk about the confusion matrix, false positives, false negatives, and all those kind of things. And the multiple risks in classification, which we were talking about earlier, the sort of estimation risk or the probability risk earlier, and the decision risk after. And next week, we'll also go over the fact that sometimes there are no probabilities, as in the SVM model, and you're basically just trying to fit a maximum margin kind of classifier over here. As you can see, this is the kind of channel which basically separates out most of the things with a 2x4. That's the basic idea behind an SVM, and that will be covered in class next week.